In this lecture, we introduce the notion of a random variable. A random variable is, loosely speaking, a numerical quantity whose value is determined by the outcome of a probabilistic experiment. The weight of a randomly selected student is one example. After giving a general definition, we will focus exclusively on discrete random variables. These are random variables that take values in finite or countably infinite sets. For example, random variables that take integer values are discrete. To any discrete random variable, we will associate a probability mass function which tells us the likelihood of each possible value of the random variable. Then we will go over a few examples and introduce some common types of random variables. And finally, we will introduce a new concept, the expected value of a random variable, also called the expectation or mean. It is a weighted average of the values of the random variable, weighted according to their respective probabilities, and has an intuitive interpretation as the average value we expect to see if we repeat the same probabilistic experiment independently a large number of times. Expected values play a central role in probability theory. We will look into some of their properties. And we will also calculate the expected values of the example random variables that we will have introduced.
We will now define the notion of a random variable. Very loosely speaking, a random variable is a numerical quantity that takes random values. But what does this mean? We want to be a little more precise, and I'm going to introduce the idea through an example. Suppose that our sample space is a set of students labeled according to their names, or for simplicity, let's just label them as A, B, C, and D. Our probabilistic experiment is to pick a student at random according to some probability law and then record their weight in kilograms. So, for example, suppose that the outcome of the experiment was this particular student and the weight of that student is 62. Or it could be that the outcome of the experiment is this particular student and that particular student has a weight of 75 kilograms. The weight of a particular student is a number little w, but let us think of the abstract concept of weight, something that we will denote by capital W. Weight is an object whose value is determined once you tell me the outcome of the experiment, once you tell me which student was picked. In this sense, weight is really a function of the outcome of the experiment. So think of weight as an abstract box that takes as input a student and produces a number, little w, which is the weight of that particular student. Or, more concretely, think of weight with a capital W as a procedure that takes a student, puts him or her on a scale, and reports the result. In this sense, weight is an object of the same kind as the square root function that's sitting inside your computer. The square root function is a function, it's a subroutine, perhaps it is a piece of code that takes as input a number, let's say the number 9, and produces another number, in this case it would be the number 3, which is the square root of 9. Notice here the distinction that we will keep emphasizing over and over. Square root of 9 is a number, it's the number 3. The box square root is a function. Now let us go back to our probabilistic experiment. Note that a probabilistic experiment such as the one in our example can have several associated random variables. For example, we could have another random variable denoted by capital H, which is the height of a student, recorded in meters. So if the outcome of the experiment, for example, was student A, then this random variable would take a value which is the height of that student. Let's say it was 1.7. Or if the outcome of the experiment was student C, then we would record the height of that student, and let us say that it turns out to be 1.8. Once again, height with a capital H is an abstract object, a function, whose value is determined once you tell me the outcome of the experiment. Now, given some random variables, we can create new random variables as functions of the original random variables. For example, consider the quantity defined as weight divided by height squared. This quantity is the so-called body mass index, and it is also a function on the sample space. Why is it a function on the sample space? Well, because once an outcome of the experiment is determined, suppose that the outcome of the experiment was the blue student, then these two numbers, 62 and 1.7, are also determined. And using those numbers, we can carry out this calculation and find the body mass index of that particular student, which in this case would be 21.5. Or if it happened that this student was selected, then the body mass index would turn out to be some other number. In this case, it would be 23. So again, we see that the body mass index can be viewed as an abstract concept defined by this formula. But once an outcome is determined, then the body mass index is also determined. And so the body mass index is really a function of which particular outcome was selected. Let us now abstract from the previous discussion. We have seen that random variables are objects, abstract objects that associate a specific value, a particular number, to any particular outcome of a probabilistic experiment. So in that sense, random variables are functions from the sample space to the real numbers. They are numerical functions, but as numerical functions, they can either take discrete values, for example, the integers, or they can take continuous values, let's say, on the real line. For example, if your random variable is the number of heads in 10 consecutive coin tosses, this is a discrete random variable that takes values in the set from 0 to 10. If your random variable is a measurement of the time at which something happened, and if your timer has infinite accuracy, then the timer reports a real number and we would have a continuous random variable. In this lecture sequence and in the next few ones, we will concentrate on discrete random variables because they are easier to handle, and then later on we will move to a discussion of continuous random variables. Throughout, we want to keep noting this very important distinction that I already brought in the discussion of our particular example, but it needs to be emphasized and re-emphasized, that we make a distinction between random variables, which are abstract objects, they are functions on the sample space, and they are denoted by uppercase letters. In contrast, we will use lowercase letters to indicate numerical values of the random variables. So little x is always a real number, as opposed to the random variable, which is a function. One point that we made earlier is that for the same probabilistic experiment, we can have several random variables associated with that experiment, and we can also combine random variables to form new random variables. In general, a function of random variables has numerical values that are determined by the numerical values of the original random variables, and so ultimately they are determined by the outcome of the experiment. So a function of random variables has a numerical value which is completely determined by the outcome of the experiment, and so a function of random variables is also a random variable. As an example, we could think of two random variables, x and y, associated with the same probabilistic experiment, and then define a random variable, let's say x plus y. What does that mean? X plus y is a random variable that takes the value little x plus little y when the random variable capital X takes the value little x and capital Y takes the value little y. So x and y are random variables. X plus y is another random variable. X and y will take numerical values once the outcome of the experiment has been obtained. And if the numerical values that they take are little x and little y, then the random variable x plus y will take the numerical value little x plus little y. So we can now move on and start doing some interesting things about random variables, characterize them, describe them, give some examples, and introduce some new concepts associated with them. A random variable can take different numerical values depending on the outcome of the experiment. Some outcomes are more likely than others, and similarly, some of the possible numerical values of a random variable will be more likely than others. We restrict ourselves to discrete random variables, and we will describe these relative likelihoods in terms of the so-called probability mass function, or PMF for short, which gives the probability of the different possible numerical values. The PMF is also sometimes called the probability law or the probability distribution of a discrete random variable. Let me illustrate the idea in terms of a simple example. We have a probabilistic experiment with 4 possible outcomes. We also have a probability law on the sample space. And to keep things simple, we assume that all 4 outcomes in our sample space are equally likely. We then introduce a random variable that associates a number with each possible outcome, as shown in this diagram. The random variable capital X can take one of 3 possible values, namely 3, 4, or 5. Let us focus on one of those numbers, let's say the number 5. So let us focus on little x being equal to 5. We can think of the event that capital X is equal to 5. Which event is this? This is the event that the outcome of the experiment led to the random variable taking a value of 5. So it is this particular event which consists of 2 elements, namely A and B. More formally, the event that we're talking about is the set of all outcomes for which the value, the numerical value of our random variable, which is a function of the outcome, that numerical value happens to be equal to 5. And in this example, it is a set consisting of 2 elements. It's a subset of the sample space, so it is an event. And it has a probability, and that probability we will be denoting with this notation. And in our case, this probability is equal to 1/2, because we have 2 outcomes. Each one has probability 1/4. The probability of this event is equal to 1/2. More generally, we will be using this notation to denote the probability of the event that the random variable, capital X, takes on a particular value, little x. This is just a piece of notation, not a new concept. We're dealing with a probability, and we indicate it using this particular notation. More formally, the probability that we're dealing with is the probability, the total probability of all outcomes for which the numerical value of our random variable is this particular number, little x. A few things to notice. We use a subscript, capital X, to indicate which random variable we are talking about. This will be useful if we have several random variables involved. For example, if we have another random variable on the same sample space, capital Y, then it would have its own probability mass function, which would be denoted with this particular notation here. The argument of the PMF, which is little x, ranges over the possible values of the random variable capital X. So in this sense, here we're really dealing with a function that we could denote just by p with a subscript x. This is the function as opposed to the specific values of this function. And we can produce plots of this function. In this particular example that we're dealing with, the interesting values of x are 3, 4, and 5. And the associated probabilities are the value of 5 is obtained with probability 1/2. The value of 4, this is the event that the outcome was C, which has probability 1/4. And the value of 3 is also obtained with probability 1/4, because the value of 3 is obtained when the outcome is D, and that outcome has probability 1/4. So the probability mass function is a function of an argument little x, and for any little x, it specifies the probability that our random variable takes on this particular value. A few more things to notice. The probability mass function is always non-negative, since we're talking about probabilities, and probabilities are always non-negative. In addition, since the total probability of all outcomes is equal to 1, the probabilities of the different possible values of the random variable should also add to 1. So when you add over all possible values of little x, the sum of the associated probabilities should be equal to 1. In terms of our picture, the events that x is equal to 3, which is this subset of the sample space, the event that x is equal to 4, which is this subset of the sample space, and the event that x is equal to 5, which is this subset of the sample space, these three events, the red, green, and blue, they are disjoint, and together they cover the entire sample space. So their probabilities should add to 1, and the probabilities of these events are the probabilities of the different values of the random variable capital X. So the probabilities of these different values should also add to 1. Let us now go through a simple example to illustrate a general method for calculating the PMF of a discrete random variable. We will revisit our familiar example involving two rolls of a tetrahedral die, and let x be the result of the first roll, y be the result of the second roll. And notice that we're using uppercase letters, and this is because x and y are random variables. In order to do any probability calculations, we also need a probability law. So to keep things simple, let us assume that every possible outcome, there are 16 of them, has the same probability, which is therefore 1 over 16 for each one of the outcomes. We will concentrate on a particular random variable defined to be the sum of the random variables x and y. So if x and y both happen to be 1, then z will take the value of 2. If x is 2 and y is 1, our random variable will take a value of 3, and similarly if we have this outcome, in those outcomes here the random variable takes the value of 4, and we can continue this way by marking for each particular outcome the corresponding value of the random variable of interest. What we want to do now is to calculate the PMF of this random variable. What does it mean to calculate the PMF? We need to find this value for all choices of little z, that is, for all possible values in the range of our random variable. The way we're going to do it is to consider each possible value of little z one at a time, and for any particular value, find out what are the outcomes, the elements of the sample space, for which our random variable takes on this specific value, and add the probabilities of those outcomes. So to illustrate this process, let us calculate the value of the PMF for little z equal to 2. This is, by definition, the probability that our random variable takes the value of 2, and this is an event that can only happen here. It corresponds to only one element of the sample space, which has probability 1 over 16. We can continue the same way for other values. of little z. So for example, the value of PMF at little z equal to 3. This is the probability that our random variable takes the value of 3. This is an event that can happen in two ways. It corresponds to two outcomes, and so it has probability 2 over 16. Continuing similarly, the probability that our random variable takes the value of 4 is equal to 3 over 16, and we can continue this way and calculate the remaining entries of our PMF. After you are done, you end up with a table, or rather a graph, a plot that has this form, and these are the values of the different probabilities that we have computed. And you can continue with the other values. It's a reasonable guess that this is going to be 4 over 16, this is going to be 3 over 16, 2 over 16, and 1 over 16. So we have completely determined the PMF of our random variable. We have given the form of the answers, and it's always convenient to also provide a plot with the answers that we have. We now want to introduce some examples of random variables, and we will start with the simplest conceivable random variable, a random variable that takes the values of 0 or 1 with certain given probabilities. Such a random variable is called a Bernoulli random variable, and the distribution of this random variable is determined by this parameter p, which is a given number that lies in the interval between 0 and 1. Using PMF notation, we have the probability of 0 being equal to 1 minus p, and the probability of taking the value of 1 equal to p. If you wish to plot this particular PMF, the plot is rather simple. It consists of two bars, one at 0 and one at 1. This one has a height of p, and this has a height of 1 minus p. Bernoulli random variables show up whenever you are trying to model a situation where you run a trial, and that trial can result in two alternative outcomes, either success or failure, or heads versus tails, and so on. Another situation where Bernoulli random variables show up is when we're making a connection between events and random variables. Here's how this connection is made. We have our sample space, omega, and within that sample space we have a certain event A, and outside the event A, of course, we have the complement of A. Our random variable is defined so that it takes a value of 1 whenever the outcome of the experiment lies in A, and it takes a value of 0 whenever the outcome of the experiment lies outside the event A, so that it lies in the complement. This random variable is called the indicator random variable of the event A. It is equal to 1 if and only if event A occurs, and the PMF of that random variable can be found as follows. This is PMF notation. This is the equivalent probabilistic notation. This is the probability that our random variable takes a value of 1. Now, the random variable takes the value of 1 if and only if event A occurs. And so what we have is that our random variable, the indicator random variable, is a Bernoulli random variable with a parameter p equal to the probability of the event of interest. Indicator random variables are very useful because they allow us to translate a manipulation of events to a manipulation of random variables, and sometimes the algebra of working with random variables is easier than working with events, as we will see in some later examples. In this segment and the next two, we will introduce a few useful random variables that show up in many applications: discrete uniform random variables, binomial random variables, and geometric random variables. Let us start with a discrete uniform. A discrete uniform random variable is one that has a PMF of this form. It takes values in a certain range, and each one of the values in that range has the same probability. To be more precise, A discrete uniform is completely determined by two parameters that are two integers, a and b, which are the beginning and the end of the range of that random variable. We're thinking of an experiment where we're going to pick an integer at random among the values that are between a and b, with the endpoints a and b including. And all of these values are equally likely. To be more formal, our sample space is the set of integers from a until b, and the number of points that we have in our sample space is b minus a plus 1 possible values. What is the random variable that we're talking about? If this is our sample space, the outcome of the experiment is already a number. And the numerical value of the random variable is just the number that we happen to pick in that range. So in this context, there isn't really a distinction between the outcome of the experiment and the numerical value of the random variable. They are one and the same. Now, since each one of the values is equally likely, and since we have so many possible values, this means that the probability of any particular value is going to be 1 over b minus a plus 1. This is the choice for the probability that would make all the probabilities in the PMF sum to 1. What does this random variable model in the real world? It models a case where we have a range of possible values and we have complete ignorance, no reason to believe that one value is more likely than the other. As an example, suppose that you look at your digital clock and you look at the time, and the time that it tells you is 11:52 and 26 seconds. And suppose that you just look at the seconds. The seconds reading is something that takes values in the set from 0 to 59, so there are 60 possible values. And if you just choose to look at your clock at a completely random time, there's no reason to expect that one reading will be more likely than the other. All readings should be equally likely, and each one of them should have a probability of 1 over 60. One final comment. Let us look at a special case where the beginning and the end point of the range of possible values is the same, which means that our random variable can only take one value, namely that particular number a. In that case, the random variable that we're dealing with is really a constant. It doesn't have any randomness. It is a deterministic random variable that takes the particular value of a with probability equal to 1. It is not random in the common sense of the word, but mathematically we can still consider it a random variable that just happens to be the same no matter what the outcome of the experiment is. The next random variable that we will discuss is the binomial random variable. It is one that is already familiar to us in most respects. It is associated with the experiment of taking a coin and tossing it n times independently, and at each toss there is a probability p of obtaining heads. So the experiment is completely specified in terms of two parameters, n, the number of tosses, and p, the probability of heads at each one of the tosses. We can represent this experiment by the usual sequential tree diagram, and the leaves of the tree are the possible outcomes of the experiment. So these are the elements of the sample space, and the typical outcome is a sequence, a particular sequence of heads and tails that has length n. In this diagram here, we took n to be equal to 3. We can now define a random variable associated with this experiment. Our random variable that we denote by capital X is the number of heads that are observed. So, for example, if the outcome happens to be this one, tails, heads, heads, we have 2 heads that are observed, and the numerical value of our random variable is equal to 2. In general, this random variable, a binomial random variable, can be used to model any kind of situation in which we have a fixed number of independent trials and identical trials, and each trial can result in success or failure, and we have a probability of success equal to some given number p. The number of successes obtained in these trials is of course random, and it is modeled by a binomial random variable. We can now proceed and calculate the PMF of this random variable. Instead of calculating the whole PMF, let us look at just one typical entry of the PMF. Let's look at this entry, which by definition is the probability that our random variable takes the value of 2. Now, the random variable taking the numerical value of 2, this is an event that can happen in 3 possible ways that we can identify in the sample space. We can have 2 heads followed by a tail, we can have heads, tail, heads, or we can have tails, heads, heads. The probability of this outcome is p times 1 minus p, so it's p squared times 1 minus p, and the other 2 outcomes also have the same probability, so the overall probability is 3 times this, which can also be written this way. 3 is the same as 3 choose 2. It's the number of ways that you can choose 2 heads where they will be placed in a sequence of 3 slots or 3 trials. More generally, we have the familiar binomial formula. So this is a formula that you have already seen. It's the probability of obtaining k successes in a sequence of n independent trials. The only thing that is new is that instead of using the traditional probability notation, now we're using PMF notation. To get a feel for the binomial PMF, it is instructive to look at some plots. So suppose that we toss the coin 3 times and that the coin tosses are fair, so that the probability of heads is equal to 1/2. Then we see that 1 head or 2 heads are equally likely, and they are more likely than the outcome of 0 or 3 heads. Now, if we change the number of tosses and toss the coin 10 times, then we see that the most likely result is to have 5 heads, and then as we move away from 5 in either direction, the probability of that particular result becomes smaller and smaller. Now, if we toss the coin many times, let's say 100 times, the coin is still fair, then we see that the number of heads that we're going to get is most likely to be somewhere in this range between, let's say, 35 and 65. These are values of the random variable that have some noticeable or high probabilities, but anything below 30 or anything above 70 is extremely unlikely to occur. We can generate similar plots for unfair coins. So suppose now that our coin is biased and the probability of heads is quite low, equal to 0.2. In that case, the most likely result is that we're going to see 0 heads, and then there's smaller and smaller probability of obtaining more heads. On the other hand, if we toss the coin 10 times, we expect to see a few heads, not a very large number, but some number of heads between, let's say, 0 and 4. Finally, if we toss the coin 100 times and we take the coin to be an extremely unfair one, what do we expect to see? If we think of probabilities as frequencies, we expect to see heads roughly 10% of the time. So given that n is 100, we expect to see about 10 heads. But when we say about 10 heads, we do not mean exactly 10 heads. About 10 heads in this instance, as this plot tells us, is any number more or less in the range from 0 to 20. But anything above 20 is extremely unlikely. Our discussion of random variables so far has involved nothing but standard probability calculations. Other than using the PMF notation, we have done nothing new. It is now time to introduce a truly new concept that plays a central role in probability theory. This is the concept of the expected value or expectation or mean of a random variable. It is a single number that provides some kind of summary of a random variable by telling us what it is on the average. Let us motivate with an example. You play a game of chance over and over, let us say 1,000 times. Each time that you play, you win an amount of money, which is a random variable, and that random variable takes the value 1 with probability 2/10, the value of 2 with probability 5/10, the value of 4 with probability 3/10. You can plot the PMF of this random variable. It takes values 1, 2, and 4, and the associated probabilities are 2/10, 5/10, and 3/10. How much do you expect to have at the end of the day? Well, if you interpret probabilities as frequencies, in 1,000 plays, you expect to have about 200 times this outcome to occur, and this outcome about 500 times, and this outcome about 300 times. So your average gain is expected to be your total gain, which is 1 200 times plus 2 500 times plus 4 300 times. This is your total gain, and to get the average gain you divide by 1,000, and the expression that you get can also be written in a simpler form as 1 times 2/10 plus 2 times 5/10 plus 4 times 3/10. So this is what you expect to get on the average if you keep playing that game. What have we done? We have calculated a certain quantity, which is a sort of average of the random variable of interest. And what we did in this summation here, we took each one of the possible values of the random variable. Each possible value corresponds to one term in the summation, and what we're adding is the numerical value of the random variable times the probability that this particular value is obtained. So when x is equal to 1, we get a 1 here and then the probability of a 1. When we add the term corresponding to x equals to 2, we get little x equals to 2, and next to it the probability that x is equal to 2, and so on. So this is what we call the expected value of the random variable x. This is the formula that defines it, but it's also important to always keep in mind the interpretation of that formula. The expected value of a random variable is to be interpreted as the average that you expect to see in a large number of independent repetitions of the experiment. One small technical caveat: if we are dealing with a random variable that takes values in a discrete but infinite set, this sum here is going to be an infinite sum or an infinite series. And there's always a question whether an infinite series has a well-defined limit or not. In order for it to have a well-defined limit, we will be making the assumption that this infinite series is, as it's called, absolutely convergent, namely that if we replace the x's by their absolute values, so we're adding positive numbers, the sum, or non-negative numbers, the sum of those numbers is going to be finite. So this is a technical condition that we need in order to make sure that this expected value is a well-defined and finite quantity. Let us now calculate the expected value of a very simple random variable, the Bernoulli random variable that takes the value 1 with probability p and the value 0 with probability 1 minus p. The expected value consists of two terms. X can take the value 1, this happens with probability p, or it can take a value of 0, this happens with probability 1 minus p, and therefore the expected value is just equal to p. As a special case, we may consider the situation where X is the indicator random variable of a certain event A, so that X is equal to 1 if and only if event A occurs. In this case, the probability that X equals to 1, which is our parameter P, is the same as the probability that event A occurs, and we have this relation. And so with this correspondence, we readily conclude that the expected value of an indicator random variable is equal to the probability of that event. Let us move now to the calculation of the expected value of a uniform random variable. Let us consider, to keep things simple, a random variable which is uniform on the set from 0 to n. It's uniform, so the probability of the values that it can take are all equal to each other. It can take one of n plus 1 possible values, and so the probability of each one of the values is 1 over n plus 1. We want to calculate the expected value of this random variable. How do we proceed? We just recall the definition of the expectation. It's a sum where we add over all the possible values, and for each one of the values we multiply by its corresponding probability. So we obtain a summation of this form. We can factor out a factor of 1 over n plus 1, and we are left with 0 plus 1 plus all the way up to n. And perhaps you remember the formula for summing those numbers, and it is n times n plus 1 over 2. And after doing the cancellations, we obtain a final answer which is n over 2. Incidentally, notice that n over 2 is just the midpoint of this picture that we have here in this diagram. This is always the case. Whenever we have a PMF which is symmetric around a certain point, then the expected value will be the center of symmetry. More general, if you do not have symmetry, the expected value turns out to be the center of gravity of the PMF. If you think of these bars as having weight, where the weight is proportional to their height, the center of gravity is the point at which you should put your finger if you want to balance that diagram so that it doesn't fall in one direction or the other. And we now close this segment by providing one more interpretation of expectations. Suppose that we have a class consisting of n students and that the ith student has a weight which is some number xi. We have a probabilistic experiment where we pick one of the students at random, and each student is equally likely to be picked as any other students. And we're interested in the random variable x, which is the weight of the student that was selected. To keep things simple, we will assume that the xi's are all distinct. And we first find the PMF of this random variable. Any particular xi that is possible is associated to exactly one student because we assumed that the xi's are distinct. So this probability would be the probability of selecting the ith student, and that probability is 1 over n. And now we can proceed and calculate the expected value of the random variable x. This random variable x takes values, and the values that it takes are the xi's, and a particular xi will be associated with a probability of 1 over n, and we're adding over all the i's or over all the students, and so this is the expected value. So what we have here is just the average of the weights of the students in this class. So the expected value in this particular experiment can be interpreted as the true average over the entire population of the students. Of course, here we're talking about two different kinds of averages. In some sense, we're thinking of expected values as the average in a large number of repetitions of experiments, but here we have another interpretation as the average over a particular population. We now note some elementary properties of expectations. These will be some properties that are extremely natural and intuitive, but even so, they're worth recording. The first property is the following. If you have a random variable which is non-negative, then its expected value is also non-negative. What does it mean that a random variable is non-negative? What it means is that for all possible outcomes of the experiment, no matter what the outcome is, the associated numerical value of the random variable is a non-negative number. What's the implication of this? When we calculate an expectation, we're adding over all the possible numerical values of the random variable. All the possible numerical values of the random variable under this assumption are non-negative. Probabilities are also non-negative, so we have a sum of non-negative entries, and therefore the expected value is also going to be non-negative. The next property is a generalization of this. Consider now a random variable that has the property that no matter what the outcome of the experiment is, the value of this random variable lies in the range between two constants, a and b. In this case, we argue as follows. The expected value, by definition, is a sum over all possible values of the random variable of certain terms. Now, the possible numerical values of the random variable are all of them at least as large as a, so this gives us an inequality of this type. Then we pull a factor of a outside the summation. And finally, we recall that the sum of a PMF over all possible values of little x is equal to 1. Why is that the case? Well, these are the probabilities for the different numerical values of the random variable. The sum of the probabilities of all the possible numerical values has to be equal to 1 because that exhausts all the possibilities. So we obtain a times 1, which is a. So what we have proved is that the expected value is at least as large as a. You can use a symmetrical argument where the inequalities will go the opposite way and where a's will be replaced by b's to prove the second inequality as well. The last fact we want to take note of is the following. If we have a constant and we take its expected value, we obtain the same constant. What does that mean? We have only been talking about expected values of random variables. What does it mean to take the expected value of a constant? Well, as we discussed earlier, we can think of a constant as being a random variable of a very special type, a random variable whose PMF takes this form. This random variable can take only a single value, and the probability of that single value is equal to 1. This means that in the formula for the expected value, there's going to be only one term in this summation, and that term is going to be c times the probability that our random variable takes the value c. Now, that probability is equal to 1, and we're left with c. So this equality makes sense, of course, as long as you understand that a constant can also be viewed as a random variable of a very degenerate type. Now, intuitively, of course, it's certainly clear what this is saying, that if a certain quantity is always equal to c, then on the average, it will also be equal to c. In this segment, we discuss the expected value rule for calculating the expected value of a function of a random variable. It corresponds to a nice formula that we will see shortly, but it also involves a much more general idea that we will encounter many times in this course in somewhat different forms. Here's what it is all about. We start with a certain random variable that has a known PMF. However, we're ultimately interested in another random variable y, which is defined as a function of the original random variable. We're interested in calculating the expected value of this new random variable y. How should we do it? We will illustrate the ideas involved through a simple numerical example. In this example, we have a random variable x that takes values 2, 3, 4, or 5 according to some given probabilities. We are also given a function that maps x values into y values, and this function g then defines a new random variable. So, if the outcome of the experiment leads to an x equal to 4, then our random variable y will also take a value equal to 4. How do we calculate the expected value of y? The only tool that we have available in our hands at this point is the definition of the expected value, which tells us that we should run a summation over the y-axis, consider different values of y one at a time, and for each value of y, multiply that value by its corresponding probability. So in this case, we start with y equal to 3, which needs to be multiplied by the probability that y is equal to 3. What is that probability? Well, y is equal to 3 if and only if x is 2 or 3, which happens with probability 0.1 plus 0.2. Then we continue with the summation by considering the next value of little y. The next possible value is 4, and this gives us a contribution of 4 weighted by the probability of obtaining a 4. The probability that y is equal to 4 is the probability that x is either equal to 4 or to 5, which happens with probability 0.3 plus 0.4. So this way we obtain an arithmetic expression which we can evaluate, and it's going to give us the expected value of y. But here's an alternative way of calculating the expected value. And this corresponds to the following type of thinking. 10% of the time x is going to be equal to 2. And when that happens, y takes on a value of 3. So this should give us a contribution to the average value of y, which is 3 times 0.1. Then, 20% of the time, x is 3 and y is also 3. So 20% of the time, we also get 3's in y. Then, 30% of the time, x is 4, which results in a y that's equal to 4. So we obtain a 4 30% of the time. And finally, 40% of the time x equals to 4, which results in a y equal to 4. And we obtain this arithmetic expression. Now you can compare the two arithmetic expressions, the red and the blue one, and you will notice that they're equal, except that the terms are arranged in a slightly different way. Conceptually, however, there's a very big difference. In the first summation, we run over the values of y one at a time. In the second summation, we run over the different values of x one at a time and took into account their individual contributions. This second way of calculating the expected value of y is called the expected value rule, and it corresponds to the following formula. We carry out a summation over the x-axis. For each x value that we consider, we calculate what is the corresponding y value, that's g of x, and also weigh this term according to the probability of this particular x. So, for instance, a typical term here would be when x is equal to 2, g of x would be equal to 3, and the corresponding probability, that's the probability of a 2, would be a 0.1. The advantage of using the expected value rule instead of the definition of the expectation is that the expected value rule only involves the PMF of the original random variable, so we do not need to do any additional work to find the PMF of the new random variable. Now we argued in favor of the expected value rule by considering this numerical example and by checking that it gives the right result. But now let us verify, let us argue more generally that it's going to give us the right answer. So what we're going to do is to take this summation and argue that it is equal to the expected value of y, which is defined by that summation. So let us start with this. It's a sum over all x's. Let us first fix a particular value of y and add over all those x's that correspond to that particular y. So we're fixing a particular y, and so we're adding only over those x's that lead to that particular y, and we carry out this summation. So this is the part of this sum associated with one particular choice of y. But in order, and it's a sum really over this set of x's. But in order to exhaust all x's, we need to consider all possible values of y, and this gives rise to an outer summation over the different y's. So for any fixed y, we add over the associated x's, but we want to consider all the possible y's. Now, at this point, we make the following observation. Here we have a summation over y's, and let's look at the inner summation. The inner summation involves x's, all of which are associated with a specific value of y. Having fixed y, all the terms inside this sum have the property that g of x is equal to y. So g of x is equal to that particular y, and we can make this substitution here. Now, when we look at this summation, we now realize that it's a summation over x's, while y is being fixed. And so we can take this term of y and pull it outside the summation. What this leaves us with is a sum over all y's of y, and then a further sum over all x's that lead to that particular y of the probabilities of those x's. Now, what can we say about this inner summation? We have fixed the y. For that particular y, we're adding the probabilities of all the x's that lead to that particular y. Fixing y, consider all the x's that lead to it. This is just the probability of that particular y. But what we have now is just the definition of the expected value of y. And this concludes the proof that this expression, as given by the expected value rule, gives us the same answer as the original definition of the expected value of y. Now, before closing, a few observations. The expected value rule is really simple to use. For example, if you want to calculate the expected value of the square of a random variable, then you're dealing with a situation where the g function is the square function. And so the expected value of x squared will be the sum over all x's of x squared weighted according to the probability of a particular x. And finally, one important word of caution, that in general the expected value of a function, so for example expected value of x squared, in general is not going to be the same as taking the expected value of x and squaring it. So this is a word in caution that in general you cannot interchange the order with which you apply a function and then you calculate expectation. There are exceptions, however, in which we happen to have equality here, and this is going to be our next topic. We end this lecture sequence with the most important property of expectations, namely linearity. The idea is pretty simple. Suppose that our random variable x is the salary of a random person out of some population, so that we can think of the expected value of x as the average salary within that population. And now suppose that everyone gets a raise and y is the new salary. And generously, the new salary is twice the old salary plus a bonus of $100. What happens to the expected value of the salary, or the average salary? Well, the new average salary, which is the expected value of 2x plus 100, is twice the old average plus 100. So, doubling everyone's salary and giving to everyone an additional 100, what it does to the average is that it doubles the average and adds 100 to it. This is the linearity property of expectation in one particular example. It's a most intuitive property, but it's worth also deriving it in a formal way. And the derivation proceeds through the expected value rule. We're dealing here with a particular function g, which is a linear function. So we're dealing with a linear function ax plus b, and we're dealing with a random variable y, which is g applied to an original random variable x. So the expected value of y can be calculated according to the expected value rule. It's the sum over all x's of g of x times the probability of that particular x. And we plug in the specific form of the function g, which is ax plus b. And then we separate the sum into two sums. The first sum, after pulling out a constant of a, takes this form. And the second sum, after pulling out the constant b, takes this form. Now, the first sum is a times the expected value of x. This is just the definition of the expected value. As for the second sum, we realize that this quantity is equal to 1 because it is the sum of the probabilities of all the different values of x. And this concludes the proof of the linearity of expected values. Notice that for expected values, what we have is that the expected value of y, which is expected value of g of x, is the same as g of the expected value of x. The expected value of a linear function is the same linear function applied to the expected value. But this is an exceptional case. This does not happen in general. It's an exceptional function g that makes this happen. This property is true for linear functions, but for nonlinear functions it is generally false.